Hello, Stat students. Today we will start Chapter 6 notes. Chapter 6 is our last chapter of this first semester, and we will continue talking about probability. In this chapter, we will talk about special type of variables called random variables that deal with probability. In the first section, we're going to talk about two types of random variables: discrete random variables and continuous random variables. A probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. And I mentioned a probability model and the criteria in the last chapter. For some definitions, a random variable, which is usually denoted by a capital letter, takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probability of occurring. So here's the discrete random variables, and that table is a probability distribution. So it gives you each of the values for your x and then what the probability is for each one. A discrete random variable, x, like I said, it's denoted by a capital letter, takes a fixed set of possible values with gaps between. So the thing to remember about a discrete random variable is it's a variable that's countable. So it's a countable number of outcomes. Nice integers, nice whole numbers. That's probably a better word. So for example, a discrete random variable would be the number of people in a family, a number rolled on a die, because you're going to have one, two distinct numbers that you get by counting. The probability distribution of a discrete random variable x lists the values known as x sub I and their probabilities known as p sub I. So if you look at the table, you have in the first row the value of the variable. So you have x sub 1 and its probability would be p sub 1, and then x sub 2's probability would be p sub 2, and so on. The probabilities p sub I must satisfy those two requirements that I mentioned in last chapter to be legitimate. Every probability p sub I is between 0 and 1, and the sum of the probabilities must equal 1. To find the probability of any event, you add the probabilities p sub I of the particular value x sub I that make up the event. All right, and let's do an example problem where you see a probability distribution and we can describe the distribution. In 2010, there were 1,319 games played in the National Hockey League's regular season. Imagine selecting one of these games at random and then randomly selecting one of the two teams that played in the game. Define the random variable, so capital X, equal the number of goals scored by a randomly selected team in a randomly selected game. The table below gives the probability distribution of X. So the top row could be the number of goals, so 0 goals, 1 goal, 2 goal, 3 goals, so on. And the bottom row is the probability of each of the goals being scored. So probability of 0 goals is 0.061 for that particular team, that particular game. Show that the probability distribution for X, So for the number of goals scored by a randomly selected team in a randomly selected game is legitimate. So it must satisfy those two requirements. If you look at the bottom row, all the probabilities are between 0 and 1. And you don't have to add this, but what I did, but in order to show it, you must write down at least some of the numbers that you're adding. So if you took the bottom row and you added several of the numbers, and of course you would want to do this to verify that it does indeed equal 1. I already did it, but it does equal 1. So that's a legitimate probability distribution. For part B, make a histogram of the probability distribution. Describe what you see. All right. So your histogram's label or your graph is labeled. So you have goals scored in a game on your x-axis and the probabilities on your y-axis. And we're going to draw a histogram. It's been a while since we've done one, but those are your bars that do touch each other. So for 0 goals, the probability is 0.061. So I'm just going to barely make it like that. And you don't have to spend so much time on making this really nicely, but 1 would be 0.154. I know I'm not going to be able to do a good job. Okay, the next one is 0.228. So about 0.3. Whoa. Okay, just kind of. Okay, next one's 0.229. It's really hard to do this when you're sitting down, but whatever. And for 4 goal score, that's 0.173. Next one, 0.094. So right here. For 6 goals, 0.04. For 7 goals, 0.015. So right here. 8 goals, 0.004. And 9 goals, just barely a line there. There we go. Describe what you see. So this is really kind of a good review describing our distribution for. So I'm going to write over here. Shape, outlier, center spread. The shape is right skewed. There's no apparent outlier. There's one peak. So our mode is between 2 and 3 goals. This is our best description based on what we're giving. And our range is 9. What is the probability that the number of goals scored by a randomly selected team in a randomly selected game is at least 6? So the probability that the goals scored at least means greater than or equal to 6. So you're going to look at these 3, or I'm sorry, these 4. So we're going to add those up. So 0.041 plus 0.015 plus 0.004 plus 0.001. And that equals 0.061. And that's your probability. So that might have seemed pretty easy, but it does get a little bit more difficult when we're talking about random variables. This is just the intro. Case in point, the back page. The mean, because I didn't mention when we describe the distribution that we can figure out the mean and standard deviation as well, and there's a formula. So the mean, which is known as an expected value of any discrete random variable, is an average, just like you would expect the mean to be, of the possible outcomes, with each outcome weighed by its probability. So there's the difference than regular means. With probabilities, you have this weighing. Here's the definition. Suppose your capital X is a discrete random variable whose probability distribution is, so you're given that table. To find the mean, which a lot of times on a test, you'll see either you'll be asked to find the mean or you'll be asked to find the expected value. It's the same thing of that discrete random variable. You multiply each possible value by the probability, then add all the products. So what you do is you multiply this times that, and then you multiply x2 times p2 and so on, and you add them all together, and you don't divide by anything, and that'll give you the expected value or the mean. All right. And now for the interpretation. So this is big. And it goes back to the definition of probability, like in the long run, or after many, many, many trials, or in this case, after many, many, many goals scored, we would expect the average, whatever. So if we perform many, many, many trials, we would expect the average, whatever the X variable is, the number of goals scored, to be blank. So that's your interpretation. And we will do a sample problem here in a bit too. The next one, since we use mean as the measure of center for a discrete random variable, we'll use standard deviation as our measure of spread, because they go hand in hand. If you're going to use the mean, use the standard deviation. The definition of the variance of a random variable is similar to the definition of the variance for a set of quantitative data. So when we found the variance of quantitative data, which we don't use that often, what we did was we took the value and subtracted the mean from it, squared it, and did it for each of the values, and then we added all of those up, and that would be our variance. Something very similar. So suppose X is a discrete random variable whose probability distribution is shown below, and that the mean of X is known as, and I didn't even mention right here, but it is, remember, the mean is like a U with a long tail in front. And this is of the random variable X. So the mean is U, is the mean of X. The variance of X, so the variance is given by the notation, this Greek letter sigma, looks like a circle with like a little tail, I guess. The variance is equal to the value minus the mean, minus the expected mean, squared times the probability for that first value. And then you do it again, second value minus the expected mean squared times P2. And then you add all of those up together, and that'll give you the variance. To get the standard deviation, all you do is you take the square root of the variance. So the standard deviation, denoted by sigma, so this is the standard deviation, you just take the square root of it. I don't really need to go any further into that. As far as the interpretation goes, again, something that I would highlight. On average, whatever the X variable is, the number of goals will differ from the mean of whatever that mean was by about a certain number. And we will do an example. Okay. And the example is right below. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales. What Apgar scores are typical? To find out, researchers recorded the Apgar scores of over 2 million newborn babies, because you have to look at lots and lots and lots of data in a single year. Imagine selecting one of these newborns at random. That's our chance process. Define the random variable X equals Apgar score of a randomly selected baby 1 minute after birth. The table below gives the probability distribution for X. So the scores of 0 all the way up to 10, and the probabilities listed for each one. This one's already done for you, so I'm just kind of going over it. Compute the mean and standard deviation of the random variable X and interpret it in context. So if you look at how to find the expected value or the mean, mu of X, you take the value times the probability plus the next value times the probability plus the next, and so on. And then you add them all up and you end up getting the mean as 8.128. So that is our expected value, or our mean of our discrete random variable. The mean Apgar score, and there's the interpretation, of a randomly selected newborn is 8.128. This is the long-term average Apgar score of many, many, many randomly chosen babies. The standard deviation is given on the bottom, and that's the square root of the variance. So notice, and we'll just look at a couple of them. You take the first value, which is 0, minus that expected mean that we just calculated, square it, and multiply by its probability, which was 0.001. So the first row, or the first column in our table, and then the second one, and so on. And it ended up being 2.066, which you would take the square root of, and you get 1.437. And on the bottom is the interpretation. On average, because remember the standard deviation is how far something is away from the mean. So on average, a randomly selected baby's Apgar score will differ from the mean of 8.128 by about 1.4. So 1.4 above or below the mean. So that's the difference. That would take a long time if we had to do it by hand. So there is an easier way to do it, and that is on our calculators. And so I will make a little second video, but honestly, I don't even think I need to. I can just tell you the steps of it. How do you calculate mean and standard deviation of a discrete random variable on the calculator? Here's what you do. You enter the X values into list 1. So remember, you go to stats, edit. So we haven't done this in a while, so you might want to write down the steps. And then you would enter the value X values into list 1. You enter the probability values into list 2. Then you do a one variable stats with list 1 in the list category, in the first category, I guess, and use list 2 as the frequency list, and then you calculate. I might go ahead and do the bottom one with you guys, actually, so I will. When you do the one variable stats, you will use X bar as your mean, even though we are using that as our expected value. But you will not see the sample standard deviation. You will see that will be left blank. You will see this as your standard deviation. And so let's just do this example. Okay, in 2010, there were 1,319 games. Oh, this is a hockey one, so I don't need to read it to you. So here's the goals scored and the probability. Compute the mean and standard deviation of the random variable X and interpret this value in context. So I did it ahead of time, and what I want to do is we'll just do the second problem on my calculator. So for this one, I went ahead and entered the goals in list 1. So I'll just tell you what I did, so you can go back and do it if you want. And I entered probabilities in list 2. And then I computed a one variable stats. And so you go under stats, and instead of edit, you go to calculate. So stats, calculate one variable stats. It's pretty easy. I mean, you really don't need me to do a second video on this. But you would just choose L2 in your frequency list. I still would like to do one just to say I've done it. Compute the mean and standard deviation of the random variable x and interpret this value in context. Okay, so ended up getting that the mean or the expected value of that random variable was x bar, or different symbol here. It was 2.851. After, because I'm interpreting it now, after viewing many NHL games, we would expect the average number of goals to be about 2.851. That's our interpretation. For our standard deviation, my standard deviation ended up being 1.63, and its interpretation, on average, the number of goals scored will differ from the mean of 2.851 by about 1.63 goals. Really work on your interpretations, because those are the harder ones. Doing the math is not the hard part in this class. It's the interpretation and how you follow through on your descriptions and process. Okay, so for this last example, I'll go ahead and do it in a separate video so that you can actually see me doing it, and then we will go ahead and just finish up the interpretation. I'll just tell you what it is and you can write it down, all right? Have a great day, stat students.